let's wrap up this discussion with a summary, a quick summary of all the properties that we've talked about of derivatives. So if f is differentiable on an interval, then f is smooth. If it's differentiable, then we get a curve that looks like this. If I have a point where it's not differentiable, then I end up with perhaps a cusp or a vertical asymptote. Either way, I'm going to end up with something that is not smooth. If the first derivative is positive, f prime is greater than 0, then f is increasing, which makes sense because if I'm increasing, then clearly my derivative function will be positive everywhere because the slope of the derivative line is positive everywhere. And likewise, if f prime is less than 0, then f is going to be decreasing. If I draw something that's decreasing, clearly the slopes of my tangent lines are going to be negative everywhere along this curve. If f prime changes sign, then f has a local minimum or a maximum, which again, if we draw it, it kind of makes sense because here the derivative is 0. Prior to it, the derivative is positive. After it, the derivative is negative. So the derivative changed sign from positive to negative. So this was a max. Likewise, here the derivative is negative, 0, positive. So I went from negative to positive, and this is a min. If the second derivative is positive, then it's concave up. We'll see if I have something that's concave up, second derivative tells me what's happening to the first derivative. The first derivative is increasing. It's positive. That gives me something that's concave up. Likewise, if the second derivative is negative, then I have something that's concave down because the second derivative is getting smaller as I move across here. So the second derivative is decreasing. So I have something that's concave down. If the second derivative changes sign, then f has an inflection point. Or, well, actually, I should leave it there as if it changes sign. And we saw what happened there, something that looks like this. Roughly in there, I'm concave down, and then I switched to concave up at this point, and that gave me my inflection point. Another candidate for that is it's true that the second derivative has to change sign, but basically you're to keep in mind that if the second derivative is 0 or undefined, that's what's going to give me the candidates for the inflection point to look to see if they change sign. If the first derivative is 0 and the second derivative is negative, then it's a local max. The first derivative 0 gives me a situation where the slope of the tangent is 0, and if it's negative, then it means concave down. Well, if it's concave down and the first derivative is 0, then I have to have a local max. And the same argument goes through here. If f prime is 0 and f double prime is positive, then it's a local min. Because if f double prime is positive, that means I'm concave up. So if I'm concave up over an interval where at this value the slope is 0, the slope of the tangent line is 0, then this must be a minimum. So in a nutshell, that is what we've been doing for the last, 8 or 10 videos.